Hey there, science fans! Today, we're diving into the fascinating world of ELISA. ELISA, short for Enzyme-Linked Immunosorbent Assay, is like a detective's toolkit for identifying tiny but important molecules called antigens. These antigens can be anything from viruses to hormones, and ELISA helps us track them down with incredible precision. ELISA relies on the remarkable ability of antibodies to bind specifically to their target antigens, much like a lock and key. This powerful technique comes in various flavors, each with its unique strengths. We'll be focusing on two popular ELISA methods: sandwich ELISA and competitive ELISA. But first, let's quickly recap the basics of direct and indirect ELISA, which lay the groundwork for these advanced techniques. Direct ELISA is the simplest form of this technique. Imagine you want to find out if a patient has been infected with a particular virus. First, a known antigen, in this case, a viral protein, is coated onto a surface. Then, the patient's serum, which contains antibodies, is added. If the patient has encountered the virus before, their serum will contain antibodies specific to the viral antigen. These antibodies will bind to the antigen-coated surface. Finally, an enzyme-linked antibody specific to the antibody in the patient's serum is added. This enzyme-linked antibody will bind to any patient antibodies that have attached to the antigen. When a substrate is added, the enzyme will cause a color change, signaling a positive result. Direct ELISA is quick and straightforward, but it can have lower sensitivity compared to other ELISA methods. Now, let's step up our ELISA game with the indirect ELISA. This method takes a slightly more roundabout, but ultimately more sensitive approach. Like direct ELISA, indirect ELISA starts with the antigen immobilized on a surface. The patient's serum is added, and any antibodies specific to the antigen will bind. Here's where it gets interesting. Instead of directly adding an enzyme-linked antibody specific to the patient antibody, we introduce a secondary antibody. This secondary antibody is designed to bind to the constant region of the primary antibody from the patient's serum. The secondary antibody is linked to an enzyme, and upon substrate addition, a color change indicates a positive result. The advantage here is that multiple secondary antibodies combine to a single primary antibody, amplifying the signal and increasing sensitivity. Indirect ELISA offers higher sensitivity than direct ELISA, making it suitable for detecting lower concentrations of antibodies. Prepare to be amazed by the sandwich ELISA, known for its specificity and sensitivity. Imagine building a sandwich with antibodies and antigens. We use two antibodies recognizing different parts of the antigen. The capture antibody coats the surface, ready to snag the antigen. The antigen binds to the capture antibody, like the first slice of bread. The detection antibody sandwiches the antigen, ensuring specificity. Section 5. Sandwich ELISA Procedure. A step-by-step guide. Let's break down the sandwich ELISA procedure into easy-to-follow steps. First, the capture antibody is coated onto the wells of a microplate. This antibody acts like a hook, grabbing onto the target antigen. Next, the remaining surface of the wells is blocked with a blocking buffer. This prevents non-specific binding, ensuring accurate results. Finally, the substrate is added. If the target antigen is present, a detectable signal is produced. Researchers can quantify the target antigen in a sample. Section 6. Sandwich ELISA. Advantages and disadvantages. Sandwich ELISA offers several advantages, making it a popular choice for various applications. First, the use of two antibodies that recognize different epitopes on the target antigen ensures high specificity, minimizing false positive results. Second, sandwich ELISA is highly sensitive, enabling the detection of even minute quantities of antigen in a sample. Third, sandwich ELISAs can be easily adapted for various sample types and target antigens. However, sandwich ELISA also has a few limitations. Finding two antibodies that bind to different epitopes on the target antigen without interfering with each other can be challenging. Sandwich ELISAs often require careful optimization of antibody concentrations and incubation times to achieve optimal performance. Despite these limitations, sandwich ELISA remains a powerful tool in diagnostics and research. Section 7. Competitive ELISA, a battle for antibody attention. Now, let's explore competitive ELISA, a technique where antigens battle it out for antibody binding sites. Imagine a game of musical chairs, but instead of chairs, we have antibodies, and the players are antigens. In competitive ELISA, the sample antigen competes with a known quantity of labeled antigen for binding to a limited number of antibody binding sites. The more antigen present in the sample, the less labeled antigen will bind to the antibodies, resulting in a weaker signal. This competitive binding allows us to determine the concentration of the target antigen in the sample by comparing the signal to a standard curve generated using known antigen concentrations. Section 8. Competitive ELISA Procedure. Unveiling the competition. Let's delve into the step-by-step procedure of competitive ELISA. First, the antibody specific to the target antigen is coated onto the wells of a microplate. Second, the remaining surface of the wells is blocked to prevent non-specific binding. Third, the sample containing the unlabeled antigen and a known concentration of labeled antigen are added to the wells simultaneously. They compete for binding to the immobilized antibody. Fourth, unbound antigen is washed away. Fifth, the substrate is added, and the enzyme linked to the labeled antigen catalyzes a reaction, producing a detectable signal. The intensity of the signal is inversely proportional to the concentration of unlabeled antigen in the sample. By comparing the signal intensities to a standard curve, researchers can accurately determine the concentration of the target antigen in the sample. Section 9. ELISA, a cornerstone of diagnostics and research. ELISA, in its various forms, has revolutionized diagnostics and research. Its applications are vast and diverse. First, ELISA is widely used to diagnose infectious diseases like HIV, hepatitis, and Lyme disease. It can also detect autoimmune diseases and certain types of cancer. Second, ELISA ensures food safety by detecting harmful contaminants like bacteria, toxins, and allergens in food products. Third, ELISA helps monitor environmental pollutants such as pesticides and heavy metals in water and soil samples. Fourth, ELISA plays a crucial role in drug discovery and development, from screening for potential drug candidates to monitoring drug efficacy and safety. As we continue to unlock the secrets of the immune system, ELISA will undoubtedly remain an indispensable tool in our quest for a healthier and safer world. That's ELISA for you, folks. Keep those scientific minds curious, and I'll catch you next time for another exciting adventure in the world of science.